We'll start with chapter 3, and chapter 3 is basically about the initial phase is about the pure substances, understanding what a pure substance is, and how do you define a pure substance or a pure mixture. And this would be followed by the phase change processes, and the focus of this chapter is on the property tables. So essentially what we'll be doing is we'll be looking into the property tables, and I would recommend that for this chapter you should have your tables with you. It's better if you have them in the hard form. So once we move on towards the later half of the chapter, you'll have an understanding of how to read the tables, and it would be convenient for you while we'll be doing the examples uh, to extract the data out of the table. So let us begin with the overview of this chapter. We'll start with the concept of pure substance. We'll try to define what a pure substance is, and based on our definition of pure substance, we'll move on towards the phase change process of a pure substance. Not all the phase change processes, but a particular phase change process will come to know why that phase change process is important for us from the point of view of mechanical thermodynamics. Then we'll try to replicate that process on pressure volume and temperature volume, pressure specific volume and temperature specific volume diagrams. By the way, do you know why we have chosen these two characteristic properties, pressure specific volume and temperature specific volume, for the process diagrams?
So, because the system is a simple compressor, means they are independent and intensive properties.
Yes, we have chosen two independent intensive properties to identify the state of the system. So on everywhere on the P specific volume and temperature specific volume diagram, you have basically the representation of states of a system. And that area basically would be representing the any change in the state of the system could be represented by a PV diagram or a TV diagram. Moving on, you'll have to understand the process of determining uh, data of pure substances from the tables of property data. So if you have to extract properties, thermodynamic properties include pressure, temperature, specific volume, internal energy, and there are few others. So you would learn how to extract the relevant data out of the table depending upon, and then you'll also learn how to use the how to decide for yourself that which table you have to use to extract the data. Then you will move on towards the hypothetical substance, which is ideal gas, and the ideal gas equation of state. Once you have the ideal gas equation of state, you will apply that equation to determine some of the typical problems for equipments or systems that involve mechanical thermodynamics. And once you have learned the process of applying ideal gas equation to solve your problems, you will then be introduced to compressibility factor, which basically determines the deviation of uh, real gases from the ideal gas behavior. So this is what would be included in this chapter. Uh, if we begin with today's session, what do you understand by a pure substance?
So I'm asking impurity now.
All right, the most common understanding is the understanding where you say that a pure substance is a substance which has which is free from impurities. But in terms of thermodynamics, that's not the correct definition. The correct definition is a pure substance has a fixed chemical composition throughout. It is not necessary that your composition is fixed to an element or a group of element. Your you define a pure substance based on the composition, and you say that a fixed a substance is a pure if the chemical composition remains the same throughout the. Uh, this also brings me to the point where it says that a pure substance does not have to be a single chemical element or a compound. It is not necessary for that. A mixture of various chemical elements or compounds would be also qualifies for a pure substance as long as the mixture is homogeneous. Is this point clear?
Yes, sir.
Yes, sir.
All right.
excuse me
If
सर,
जी जी जी
एक्सक्यूज मी सर, ये केमिकल कंपोजिशन तो ये वर्ड तो फिर आप सिर्फ एक ही एलिमेंट के लिए यूज कर सकते हैं ना?
केमिकल कॉम्पोजिशन, और राइट, लेट मी टेल यू, वाटर की केमिकल कॉम्पोजिशन क्या है?
2:1।
नहीं, 2:1 में एक एलिमेंट है, दो
दो है लेकिन कंपाउंड तो एक है ना सर?
तो a pure substance does not have to be a single chemical element or compound. वाटर में मोर देन वन एलिमेंट्स आ गए,
यस सर।
ऑलराइट। कंपाउंड को भी देख लेते हैं। व्हाट डू यू थिंक अबाउट एयर? इज एयर अ प्योर सब्सटेंस?
नो सर।
आपके पास एयर जो आपके रूम में है, उसमें नाइट्रोजन कितने परसेंट है?
70।
रफली 78। ऑक्सीजन कितने?
91.
यही एयर की कॉम्पोजिशन है रफली। जी, आर यू स्टिल देयर?
यस सर, यही है।
यही है। अच्छा, और अगर आपके क्लासरूम में जो एयर होगी उसकी कॉम्पोजिशन क्या होगी?
रफली यही होगी।
Is it a mixture of compounds? Here,
यस सर।
the chemical composition is same irrespective of where you're taking the sample from.
यस सर।
So is it a pure substance or not?
यस सर, मे बी।
Got the point?
यस सर, थैंक यू सर।
All right. As it says, air, which is a mixture of several gases, is considered to be a pure substance. Why? Because the mixture is homogeneous. Homogeneous means whether you take the sample from this room over here or some other room from over here or from wherever you want to take, the ratio of nitrogen to oxygen would be the same, or the composition of the components in the air would remain the same. What about a mixture of oil and water? Is it a pure substance?
नो सर, दिस इज नॉट होमोजेनियस, आई थिंक।
Is it clear to everybody why the mixture of oil and water is not a pure substance?
Yes, sir.
So when you have a mixture of oil and water, water would settle down at the bottom due to its density. Oil would come onto the top. So if I take a sample from this region, it would be rich in oil. If I take a sample from this region, it would be rich in water. So essentially, the two samples would not be having the same composition. So this mixture is not a homogeneous mixture. Therefore, we cannot uh, reflect to this system or this mixture to be a pure mixture. Clear enough?
यस सर। एक्सक्यूज मी सर, डू वी हैव एनी स्टैंडर्ड और रेफरेंसेस in order
Sorry,
to decide a substance to be pure or not?
what do you mean by references?
Standards, I mean tables. If we are to decide whether the air is pure or not, do we have to compare with
The
the data?
basic definition is where does the table comes from? I mean, I don't understand the need of a table.
एक्सक्यूज मी सर, अगर नाइट्रोजन की वो जो एवरेज है 78 है, अगर किसी एरिया में पोल्यूशन ज़्यादा है तो 78 से अबव जा रही है, तो उसको
जी
हम
जी।
फिर तो उसको
So
प्योर कहेंगे कि नहीं?
why do you call it pollution? What is meant by polluted? What is meant by polluted? Polluted क्या होती है चीज?
इम्प्योर सब्सटेंसेस।
Got the point?
ओके।
Moving on, it says that mixture of two or more phases. Now we have two or more phases of a pure substance is still a pure substance as long as the chemical composition of all the phases is same. The primary phase, let's say you have ice and water, mixture of ice and liquid water. Is it a pure substance?
Yes, sir.
All right. Why? Because ice is in solid phase, water is in liquid, water is obviously in liquid phase, but the composition is the same, H2O. So the mixture of ice and water would still be a pure mixture or pure substance. What about a mixture of liquid air and gaseous air? Consider that you have a room in which you have air and you start liquidifying air. So let's say I am at minus 50 degrees centigrade or minus 100 degrees centigrade for that matter. I have a mixture of liquid air and gaseous air. Would I refer to that mixture as a pure mixture or an impure mixture?
Pure mixture.
Who said pure mixture?
सर अब्दुल्ला सर इस केस में कि अगर जो लिक्विफाइंग टेम्परेचर है वो सारी गैसेस का अचीव किया हो
G. That's the condition. Normally, the components would liquidify at different temperatures. So unless and until you have all the components being liquidified, you will not have a homogeneous mixture or homogeneous composition. Uh, Again, even if you have liquefied, Abdullah, liquid
यस सर
nitrogen may not have the same density as liquid oxygen. All right. So they may
यस
not
सर
mix together in the same homogeneous manner as they are in the gaseous phase. All right.
यस सर
So liquid air and gaseous air in a mixture would not be a pure substance. Why? Because in the liquid air, the composition would not be the same. Number one, due to the reason that the components would be condensing at different temperatures at a specified pressure, and number two, the densities might differ so that they may not be in the same ratio throughout the system. Clear enough?
यस सर
Right. Phases of a pure substance, again, substance exists in different phases. You already know that at room temperature pressure, copper is solid, mercury is liquid, and nitrogen is in the gaseous phase. However, under different conditions, each appear in different phase. You already know that copper at about 1300 degrees centigrade would be in the liquid form. Similarly, nitrogen at minus 196 would be in the liquid form. So it depends upon the temperature and pressure you are referring to, state of a or the phase of a particular substance. You already know that there are three principal phases. Three principal phases include within the principal phase. There are several phases that may exist, and each different phase would have a different molecular structure. For example, carbon, which is solid, the principal phase is solid, may exist in graphite in the form of graphite, which has an hexagonal crystal structure, and diamond, which has a tetrahedral crystal structure. By the knowledge of material science, you already know that iron, which is uh, iron or steel, which is in solid form, it can exist in FCC crystal structure or BC structure. It can exist as ferrite and austenite. So depending upon the structure or the atomic arrangement, atomic or molecular arrangement, depending upon what you're talking about, you may have different structures, and those structures would ultimately correspond to different phases. A phase is identified as having a distinct molecular or atomic arrangement that is homogeneous throughout the material and is separated from other phases by an easily identifiable boundary or surfaces. For example, the two phases of H2O in iced water. Ice would have its own molecular structure, water in the liquid state would have its own molecular arrangement, and there would be the distinction between the two would be the boundary of the interface between the solid and the liquid phase. Is this point clear?
यस सर
All right. Moving on, you're not concerned about what is exactly the molecular structure and how does the phases behave, different phases behave. Understanding of the molecular phenomena which is common in each phase, that is important, and you already know that. We'll just quickly go through that. It says that intermolecular bonds are strongest in the solids and they are weakest in the gaseous phase. uh, if you start with the solids, you know that the molecule in solids are arranged in a 3D pattern that is repeated throughout the lattice. That's a unit cell which is being repeated throughout the cell. And there are small distances between molecules in solid, and the attractive forces of molecules are large, and they act on each other. Now, considering the attractive forces of molecules are large, you may have a question, why don't they fall upon each other and then start piling upon top of each other? That is due to the repulsive forces that becomes dominant as the molecules start to approach each other. So as there are two molecules over here or two atoms over here, as they try to get much closer, their electron clouds start repelling each other, so that there is a specific distance at which these atoms remain, or they don't pile up on top of each other in case of solids. Solid molecules, you already know, they cannot move, but they vibrate at equilibrium positions, and the velocity of oscillations basically depend upon the temperature at which you are having that substance. As you increase the temperature, the velocity of molecules would reach to a point where the intermolecular forces would essentially overcome each other, and groups of molecules start breaking away. This is basically the melting process or the phase change process. And the molecular spacing in liquid phase is not much different from that of solid phase, but the molecules are no longer at fixed positions relative to each other. They can rotate and they can translate freely. You already know that by high school physics. Moving on, the intermolecular forces are weaker in liquids as compared to solids, but they're still stronger as compared to the gases. And in the gaseous phase, the molecules are far apart from each other, and the molecular order is essentially non-existing. They continue to move randomly, colliding with each other and the walls of the container in the gaseous phase. In the phase of pure substance, the molecules in solid are kept at positions, and then it's being like they are attached with the springs, having intermolecular forces. So these are the atoms of a solid, and it is assumed that they are vibrating at their positions, but they're not allowed to uh, move freely from their positions. However, in liquids, chunks of molecule break away from each other. They are moving freely around. But in gaseous phase, there is no specific pattern or order that is being followed by the atoms or the molecules of the gaseous phase. Now, the phase change process of pure substance. It is essential to understand the phase change process of a pure substance. There are many practical situations where two phases of a pure substance coexist in equilibrium. So, uh, from the perspective of thermodynamics of mechanical engineering, the phases which are important to you is is the liquid vapor phase. These are the two phases which are important to you. For example, water exists actually vapor involved, whether water gets the heat and evaporates. So there's a phase change process from liquid to vapor that is being involved in the boiler. Similarly, in the condenser of a steam power plant, there is the opposite phase change process. Vapor is essentially converting into liquid. So liquid and vapor to liquid phase transformation. It is very much common in many of the equipments that involve thermodynamic principles. And another example is that of the refrigerant. The refrigerant that circulates in the freezer compartment. Basically, the refrigerant turns from liquid to vapor as it extracts heat from the components. Is this point clear to you?
Yes, sir.
Yes, sir.
All right. So most of the thermodynamic principles with regards to the interest of mechanical engineering, they have essentially liquid to vapor phase transformation process or vapor to liquid phase transformation process, which is common to them. So it is essential that from the point of view of this course, you should have an understanding of the liquid and vapor phases and their mixture, and you should have an understanding of how the phase transformation process essentially initiate in these systems. However, familiar substance, which is water, is used to demonstrate the basic principles involved during the phase change process for water. And once you have learned the basics of that process or the physics of that process, what is happening in the phase change process in water, that basic principle would be applicable to all the pure substances. All pure substances would essentially exhibit the same generic behavior. So far, is it clear?
Yes, sir.
All right, moving on. So let's say I have a piston cylinder device which contains liquid water at 20 degrees centigrade and 1 atmospheric pressure. At this condition, my water should be in which phase?
Liquid phase, sir.
All right. So it says that under these conditions, your water is in the liquid phase. This liquid is also known as compressed liquid or subcooled liquid. And what is the definition of a compressed liquid or subcooled liquid? It's a liquid which is not about to vaporize. The essential thing is it is not about to vaporize. What is meant by not about to vaporize? If I add small amount of heat to this liquid, what would happen?
Sir, temperature increase हो जाएगा उसका.
G. But would it vaporize? Let's say I add
No, sir.
certain, all right, let's say I add certain amount of heat to the system. As a result of this heat addition, what would happen to this piston? Move upwards?
Sir, in case of water,
No, no. If I add some heat into the system, if I'm adding heat into the system, the outside pressure is 1 atmosphere, and then there is this weight acting on top of this water. If there is no additional force that is being acting, if there is no additional force acting on this system, increasing the heat to the system would result in what?
increase in pressure.
Increase in pressure if the volume is kept constant, or if the volume is not kept constant, pressure is kept constant, so it will do some work.
It will do some work and it would acquire some new position.
Yes, sir.
That means the specific volume would increase. All right.
Yes, sir.
So with
Yes, sir.
increase in temperature, if you increase the temperature, the specific volume would increase. Let's say to 40 degrees centigrade. Clear?
Yes, sir.
But has the water vaporized as yet?
No, sir.
No, sir. No,
No,
sir.
sir. All right. So the liquid would be termed as compressed liquid. All right. Compressed liquid, normally compressed liquid, or you can also refer to it as subcooled liquid. So a liquid which is not about to vaporize. That means if you add small amount of heat to it, it will not vaporize. That liquid is basically termed as compressed liquid. Clear enough?
Yes,
Is
sir.
this point clear? All right. Moving on, let's say this is the same thing that if now heat is being transferred to, let's say, such that the temperature goes to 40 degrees centigrade, liquid water would expand and its specific volume would increase. To accommodate this expansion, the piston moves slightly upwards. The pressure in the cylinder remains constant at 1 atmospheric pressure because the barometric pressure, which is outside pressure, and the weight of the piston is the same. And water is still a compressed liquid at this state since it has not started to vaporize. So we'll still refer to this water as compressed liquid. But let's say I increase the temperature to 100 degrees centigrade. I'm adding more heat to the system so that the temperature kept rising until it reaches to 100 degrees centigrade. And at this point, the pressure is obviously the same because you have not added any extra pressure on the piston. At this point, water is still a liquid, but any further addition of heat would result in what?
Vapors.
It would
Boiling of the
result in
water.
the, yes, it would result in the formation of vapors or vaporization. That
Yes, sir.
is a phase change process from liquid to vapor is about to take place. A liquid that is about to vaporize is called saturated liquid. Is this point clear?
Yes, sir.
Yes.
All right. So this is a liquid state. This one was state one. This is state one, 1 atmospheric, 20 degrees centigrade. You have liquid water. This is again state two, where you have liquid water, but it is at 1 atmospheric at 100 degrees centigrade, and the specific volume has increased as compared to the state one. This liquid is known as saturated liquid. Now I'll not be able to complete it because it's this whole process. So I'll stop over here and I'll begin from the same point so that we have a continuation for the next class. All right.